Hello, my name is Yaroslav and I'm presenting factorized world models for learning causal relationships. This is joint work with Artyom Zholos from Moscow Institute of Physics and Technology and Alexander Panov from Artificial Intelligence Research Institute. We want to present cause-effect modeling agent, in short CEMA, the model-based reinforcement learning agent with structured world model designed for solving out-of-distribution tasks in visual control setting. CEMA is able to learn causality between changes in robot state and changes in object state. Its world model takes as input segmented images of environment, and its latent state is factored into robot and object states. Both actor and object have their own dynamics connected via influence vector. Many visual control tasks have the following features. There is a single directly controlled by actions manipulator. There are a number of objects not controlled by agent directly, and successful completion of tasks involves some type of interaction between actor and object, for example, opening the fridge. We introduced the object-oriented structure to world model by factoring it. Let's take a look at SRSM world model used in DREAMA. It has a single dynamics model and a single latent state, representing the state of the whole environment. In CEMA, we split dynamics model on two parts, robot dynamics and object dynamics. For robot dynamics, we let the SRSM without any changes, since the robot state is controlled directly by actions. From imagined robot latent state, we predict the task-specific influence vector, which represents the collateral object control performed by a robot. The next object state is predicted using RNN and the imagined influence vector. The influence vector is also used to predict step reward. The inference model of actor remains unchanged to DREAMA. Specifically, the robot state is inferred from its previous state and current robot observation. Object latent state, on contrary, is inferred from the object image alone. For influence vector, posterior distribution is conditioned on both object and robot latent states to reflect the changes made to object by robot. Value function is conditioned on all latent states, while policy is conditioned only on robot state and low-dimensional task context vector. The training process of CEMA is the same as in DREAMA. First, the agent collects experience, interacting with the environment. Then, this experience is used to perform self-supervised training of world model. Finally, using the world model, the actor-critic policy is learned on imagined trajectories. The process is then repeated, and all three steps can be performed in parallel. For evaluating the generalization capabilities of algorithm, we built a custom parameterized task environment. It is a drawer, which should be opened by a robotic hand. In each specific task, the position of drawer is fixed. The set of tasks then coincides with the set of positions of the drawer, which is a circle with a given radius. Each observation consists of two parts: the unoccluded object image and the robot image. The performance of CEMA on training tasks is slightly worse than DREAMers in terms of task solving speed. However, its generalization capabilities are better. CEMA is able to solve more out-of-distribution tasks than DREAMA. To show how the model can reflect the cause-effect relationships, we study the excitement measure for each conditional distribution, in other words, conditional mutual information between input and output of state distributions. Results show that distributions are activated in bottom-up fashion from robot to object part, propagating influence of actions on object. Also, we conducted the experiment involving stopping the robot hand while it has just begun closing the box. Just after resuming, the robot continues to attack the drawer, which results in even faster response in influence state, which in turn affects the object state. If you're interested in our model, you can find paper, code, and presentation slides in our GitHub repository. Thank you!